Good evening once again. As Bob was just saying, back in spring of this year, I gave you parts 1 and 2 of exploring the solar system, talking about how we use spacecraft to explore, robots on Mars and sending spacecraft to other planets. This is exploring the solar system part 3, looking at how we can use telescopes, either here on Earth or fairly close to Earth, to look out into the universe and see what we learn about the solar system in which we live. So I'm going to be talking about, very briefly, the 400 years of telescopes, having a quick look at the very early images from, the fairly early views from telescopes, and views from the more recent telescopes. And then I'll be asking the usual question for these short talks: what's next? What's in the immediate future? So let's just remind ourselves how the last 400 years has gone. Galileo didn't invent the telescope, but he was one of the first to take the newly minted telescope and point it at the night sky and see what he could see. And he was one of the first that not only used the telescope to point at the night sky, but also record and document what it was that he saw. Since then, telescopes have been getting larger and larger. Back in the day, we couldn't really distinguish between amateur telescopes and professional telescopes. These days, it's a little clearer to make that divide. But throughout history, especially the last couple of centuries, telescopes have been getting larger and larger. And by that we mean the aperture, the collecting area, has been getting larger. Lenses, back in Galileo's day, lenses a few centimeters in diameter, but then they grew larger and larger, up to about the size of a meter or so, the largest lens. And then telescopes changed to using mirrors simply because they are easier to make. But they've always been getting larger and larger because the advantage of a telescope with a large aperture is not only do you collect more light, so you can see fainter objects, but you also get clearer images of those objects. So either for the planets or for distant nebulae or distant galaxies, the larger apertures give you more clear views. So it's fainter, which usually means more distance in the case of looking out into the universe, as well as the detail that you can see. And one of the largest telescopes in the world, certainly the largest telescope in the world when I was born, was this one, the 200-inch telescope with a 5-meter or 200-inch diameter mirror. So the mirror at the bottom there, the bottom of that structure, 5 meters in diameter, about the size of this room. If you think of the collecting area of that mirror, about the size of this room. The largest telescope in the world when I was born, the largest telescope in the world for most of my childhood, and indeed it was actually the largest telescope in the world for a fair chunk of my adult life. It remained the largest telescope in the world for about half a century, which is pretty amazing for any piece of scientific equipment. It has since been overtaken, and we'll come shortly to a statement about the largest telescope in the world at the moment. But of course, in the last few decades, we're used to the idea of not only having telescopes here on Earth, but having telescopes in space. So back in 1990, the Hubble Space Telescope was launched and placed into Earth orbit. So this venerable old lady is now 35 years old, which is pretty amazing that after 35 years, it's still going and it's still producing amazing images. It hasn't been replaced in the sense that, yes, the James Webb Space Telescope came along and was launched on Christmas Day 2021, but the James Webb is, strictly speaking, not a replacement for the Hubble Space Telescope. It's a complement to. The Hubble tends to work in the visible part of the spectrum. The James Webb Space Telescope works in the infrared part of the spectrum. So they will work alongside each other until one day the Hubble breaks. It relies on gyros to point it to the right part of the sky. Eventually those gyros will fail and the Hubble will be no more. But after 3.5 decades, it's still going strong. Let's hope it's good for at least another half decade, if not more. So as well as space telescopes, We're not ignoring the fact that telescopes are getting larger and larger here on Earth, and it won't be long, a couple of years or so, before this monster telescope comes along, the European Extremely Large Telescope. Ridiculous name, because astronomers are not very good at naming things, but it is extremely large because the mirror here, which is not a single piece of glass coated in metal, it's lots of smaller segments that are put together to make a larger mirror. But the effective size of the mirror when it's finished is about 39 meters. So it dwarfs anything that is a mere size of this room, 5 meters or so in diameter. And that will be coming along, should be coming online 2028 probably, so another couple of years yet. So things have continually moved on. Let's just remind ourselves when Galileo pointed his telescope for one of the first times at the objects in our solar system, which is what these talks are all about, not distant galaxies, not nebulae, but what's going on in the solar system. What did Galileo see when he first pointed his telescope at the planets? When he looked at Jupiter, he noted that our own eyes show us 4 stars which wander around Jupiter, as does the moon around the Earth. He noted, rather importantly, that this is evidence that not everything seems to rotate around the Earth. The Earth is quite definitely not the center of the universe, because some objects seem to think that Jupiter is the center of the universe. Some objects rotate around Jupiter, not around the Earth. So this was a very important observation. He made a note of it in various journals, indicating that we've got Jupiter and a number of small dots. He very quickly determined those dots weren't simply background stars, because he noted night after night after night, even though Jupiter moved slightly relative to the stars, these 4 dots moved with Jupiter. And night after night after night after night, he noted how these dots moved and deduced that they were, in a sense, a little mini solar system. Moons going around Jupiter, much like planets go around the sun, as we now know, but as was thought at the time, everything going around the Earth. So a very important observation. When Galileo pointed his telescope at Saturn, well, things got rather confusing. He wasn't sure what he was looking at. So again, the first sight that I had of Saturn was of 3 round stars, that in the middle considerably larger than the 2 lateral ones. So does that mean Saturn is actually 3 objects? Even though it appears to be a dot in the sky, when you look in a telescope, you find 3 objects. Now we now know that's because telescopes had a finite resolution, and because of the quality with which the first lenses could be ground, there were rather a lot of aberrations, and so the sort of clear views that we're used to with modern telescopes, whether they be amateur or professional, they weren't afforded to the very early astronomers, and so their views of any object were subject to the distortions of an imperfect lens. So Galileo saw an object that he thought was, well, what is it? Is it 3 objects? Is it an object with 2 absolutely enormous moons right next to the planet? Other people looked with their telescopes at Saturn and were equally confused, and the number of different versions of Saturn in the next few decades was quite large. Are we talking about a planet? Are we talking about a planet with ears? Are we talking about a planet with handles on either side? Are we talking about a planet with moons? A huge amount of confusion, and it was only a few decades later that Huygens proposed, well, I think all of this is explained by the fact that what we're actually looking at is a globe, a sphere, around which there is a flat ring system. Didn't understand what it was made of, but that was the geometry that was assumed after a few decades, and the fact that people have seen various things is simply a result of imperfections in the telescope. And of course, the idea that Saturn is actually a globe surrounded by rings, that's borne out by more modern observations such as the Hubble Space Telescope, which shows that Huygens in 1650s was effectively precisely right. It is a sphere surrounded by a ring system. Only more recently have we come to the conclusion the ring system is not a solid ring, it's actually a huge number of tiny icy particles all independently orbiting around Saturn. So that confusion eventually got sorted out. But there has been many examples of confusion in looking at the solar system since then. For instance, Schiaparelli looked at Mars and said, this is interesting, I can see all sorts of features on Mars through my telescope. And if we look at his notebook, I love the idea that his notebook has got little half pages pasted in. What did he use to paste them in? Little half stamps to make sure that he didn't even waste a full stamp. He took a stamp, cut it in half, and used that to actually paste in a little addendum to his notebook. But again, like Galileo, he tried to record everything that he saw, including features on Mars. And if we blow them up on the right-hand side, he was convinced that he could see linear features on the surface of Mars, as well as ice caps, as well as dark regions and light regions. He saw these straight lines, which in Italian ended up being called canali, channels. So he was making no comment about what formed those channels. He just said there seemed to be these straight lines. But unfortunately, he and then many others said, well, yes, these canali, these channels appear to be present. And originally in the 1880s, Schiaparelli and others said he saw these things, and then there was a little bit of, well, if he can see them, then I can see them. And then everybody who looked at Mars was convinced that, yes, we definitely have these channels. But unfortunately, channels got mistranslated as canals when some people looked at it in English. And one person in particular, Percival Lowell, in the late 1890s and early 1900s, took up this idea of, well, if there are canals on Mars, canals are obviously artificial, and they must have been made by the locals, whoever they are. Martians must have made these canals. And that's why we're familiar with the idea of Martians. We're familiar with the idea of the science fiction of the age, War of the Worlds, H.G. Wells, etc. And here we have Percival Lowell making a comment to the New York Times in which he says, there can be no doubt that living beings inhabit our neighbor world. It's interesting that at the top there it says Professor Percival Lowell, recognized as the greatest authority on the subject. I'm not sure who recognized him as the greatest authority on the subject. Maybe he did. He certainly believed, and he was absolutely convinced, that the canals were there. The canals were artificial. They were built by Martians for irrigation purposes, and intelligent beings inhabit Mars. Whether or not they are Martians that are likely to invade Earth, well, certainly that's what the science fiction of the time was saying. But Percival Lowell used this particular telescope in what's now called the Lowell Observatory in Flagstaff. This is a large refractor, and so a lot of light was collected at the business end of the refractor, and all the light was focused down to a relatively small eyepiece. There's Lowell at the business end, the eyepiece end of the telescope. And what's thought most likely is that an awful lot of light was collected by this large lens, objective lens at the end of the telescope, focused down to a relatively small eyepiece, and then the observer would have had this relatively bright light shining in their eye. What happens when you go to the optician and they shine a very bright light in your eye? You see the blood vessels on the back of your eye. And perhaps that's what a lot of people were looking at. They were trying to see detail on the surface of Mars. They were being influenced by the fact that other people said they could see canali or channels or canals. And when they saw a flash of a blood vessel or something, they thought, oh, I've just seen one as well. And the seeing is coming and going, and they couldn't necessarily pin down exactly what they were seeing, but maybe the appearance of a blood vessel made them say, oh yeah, I can see the same. And it was that, if you'll forgive the expression, hysteria behind seeing canals that tended to produce all of the observations. So Schiaparelli and others said, yeah, I can see features and I can definitely see straight lines. But as years went by, more and more people said, well, yeah, I can see the features, I can see the dark and the light, but I'm not sure I can see straight lines. Are you actually drawing straight lines where none existed? So I can see light and dark and I can see features, but no, I can't see any straight lines that you claim are there. And so the idea of a Mars covered by dark and light patches and canals eventually gave rise to the sort of image that we understand today. That's a very much more recent one, taken with the Hubble Space Telescope, in which we can see the light and dark features and we can see the ice caps, etc. But sorry, there's no sign of actually straight lines. That was purely a figment of the imagination and possibly the physiology of how light behaves when it's shining on the retina of the observer. So a bit of a shame, but no canals on Mars, no Martians. Oh well. Amateurs, of course, will want to buy telescopes. And again, there's always this drive behind wanting the largest aperture telescope to give us more light and to give us more detail on objects. So there are a number of different telescopes that are available to amateurs. On the left-hand side, we have dioptric or refracting telescopes, in other words, using lenses to collect the light. On the right-hand side, catoptric, meaning using mirrors to collect the light. And it's still fairly popular to have some telescopes, the overlap in that Venn diagram there, where some telescopes use lenses and mirrors in combination, and they go still by the rather awkward name of catadioptric, but most people just call them cats. So we have refractors, reflectors, and cats, and people will start usually with small telescopes that they can afford, and as their pockets get deeper, they will want to get larger and larger telescopes, either if their back garden allows, or sometimes if their spouse allows them to buy a telescope that's larger and larger. And there's almost no limit to how far you can go as an amateur. I mean, this is one of the largest amateur telescopes that is available. And if you're having trouble with the scale of that, let me just show you what size it is. It is a huge, great thing, very massive. But don't worry, the manufacturers of these telescopes know that it's very massive, so they'll make sure that your bank balance is a lot lighter to compensate for that. So yes, a small mortgage is required for an amateur telescope like that. So they don't sell many of them, but yes, amateurs do spend tens of thousands of pounds or dollars on their hobby once it starts to grip them. And aperture fever is not limited to amateurs, it's the same for professionals. They always want to collect more light, larger and larger apertures, and they always want more detail, which again goes with larger and larger apertures. So this is simply a graphic showing to scale various mirror sizes, not since Galileo. The smallest telescope in this particular diagram in the top left-hand corner is not Galileo's lens of a few centimeters in diameter. It's the largest refracting telescope in the world with a lens 1 meter in diameter. So that tiny dot in the top left there is a 1 meter diameter lens. And just to give you an idea of scale, there's peeking into the bottom left, a tennis court, there's a basketball court, and there's a human to scale. Okay. So the largest telescope in the world at the moment is that one, Gran Telescopio Canarias. We can't, strictly speaking, talk about diameters because big mirrors these days are made of a honeycomb of lots of smaller segments, usually hexagonal, and those small segments are put together to make a larger mirror. But if you imagine it as being circular, then it would be a mirror about 10 meters in diameter, considerably larger than this room. So that's the world record at the moment. The largest telescope in the world is sitting on the Canary Islands. If you compare that with the size of telescopes that have been into space, well, there's obviously a restriction in that we would like to have really big telescopes in space, but there are restrictions. So the space telescopes are indicated in the bottom left-hand corner there. Hubble was limited by the fact that the Hubble Space Telescope in its entirety had to fit inside the cargo bay of the shuttle, because that's what launched it. And for the James Webb Space Telescope, a somewhat larger mirror, but everything had to be folded up into a piece of huge origami in order to make sure that it could fit on top of a rocket to be launched out, not into Earth orbit, but at a location 1 million miles away where it is currently studying the universe. In addition to the space telescopes, we're building larger and larger telescopes here on Earth. As you can see, these simply from the scale, if you look towards the right-hand side of this graphic, you can see mirrors are getting absolutely ridiculously large. We've already had the very large telescope, so when they decided to build one with a 40 meter or 39 meter diameter mirror, they had to come up with a different adjective. Very large was taken, so they came up with extremely large. Yeah, limited imagination. But again, if you simply compare it with the size of a human or a basketball court, you can see 39-meter diameter mirror is absolutely huge. So that I thought was large back in the day. A telescope with a 5-meter diameter mirror I thought was impressively large. It's just difficult to get your head around how large these new ones are going to be when they come online. America are planning a 30-meter telescope, and the Europeans are already building a 40-meter telescope. Where are they situated? Well, the best observatory sites in the world tend to be on top of volcanoes, not universally, but atop of a volcano is quite a good place to put a telescope because there's not that much atmosphere above you, and volcanoes, especially in the middle of the ocean, tend to be stable weather systems. So Hawaii is a good place to put telescopes. The winds there brush over the tops of the volcanic peaks and give you nice stable air currents. The same is true for the volcanic islands of the Canary Islands. La Palma and Tenerife have some of the largest telescopes in the world. And the third site is the Atacama Desert. Again, very high, relatively dry, so you're above most of the atmosphere, and more importantly, you're above most of the water vapor. So a little bit of light gets absorbed, a little bit of light, it's still turbulent, so very little light is absorbed, but some of the light does get distorted by passing through the Earth's atmosphere. So even the Atacama Desert, which is considered to be one of the best places in the world, even that is not perfect as far as we're still looking through the Earth's atmosphere. If we have a look at a mountaintop in South America there, that's one observatory as photographed by the neighboring mountaintop, which is another observatory. There's lots of observatories on mountaintops throughout the Atacama. And although it might look a little bit hazy in the background, you think that doesn't look great, bear in mind the telescope is sitting above the haze and above the clouds. So yes, there is a weather system still throughout Chile and Peru and other South American countries, but these observatories are on mountains that are high enough that you're above most of the effects of the water vapor and the clouds, etc. So you get essentially clear nights virtually every clear night. If that isn't good enough for you, if you want, for instance, with infrared, you still don't want that atmosphere absorbing your infrared, you want to get even higher than a mountaintop. How do you get higher than a mountaintop? Well, you put the telescope in the back of a 747. So here, there's an infrared telescope in the back. You can see it, that hatch at the back there. There's an infrared telescope in the back, and then the 747 simply flies at 10 or 12,000 meters. That's not above all of the atmosphere, but it's above a pretty big fraction of the atmosphere. It's higher than any mountain. And so you get the advantage of not only reasonably stable air, you also get the advantage that there's very little water vapor above you to absorb the infrared light. So that's one of the ways that infrared astronomy was done up to about last year. Because now we have an even better infrared telescope in the James Webb sitting out in space 1 million miles away. And so this particular 747 was decommissioned last year. Watch out on eBay because it might be coming up. It's only about 100 million or so if you want to club together. I mean, if you start a raffle now, you might be able to go for it. And of course, that's the way to go. If you want to get away from the Earth's atmosphere, if you don't want to absorb anything in terms of light, and if you don't want the turbulent effect of the Earth's atmosphere distorting your images, if you want the maximum clarity, then you go above the atmosphere completely, which means you go into Earth orbit. Strictly speaking, the Hubble Space Telescope is still inside the atmosphere because the atmosphere doesn't end, it just gets thinner and thinner and thinner and thinner. So the Hubble Space Telescope at the height of a few hundred kilometers is still inside the Earth's atmosphere, but there's very little above it to distort any of its images. And the James Webb Space Telescope, even further out, again, we see it being built there on the left-hand side, a huge 5 to 6 meter diameter mirror. It had to be tested on the ground and then folded up into a tiny package, like in the middle pane there, in order that it would fit inside the fairing of a rocket, and then it was launched on Christmas Day 2021. If we have a quick look at what we've learned from Hubble and the James Webb Space Telescope, when we look at planets, we see that, for instance, when we look at Jupiter, not surprisingly perhaps, we get a complementary view. The visible part of the spectrum doesn't tell us quite the same as the infrared part of the spectrum. So Hubble on the left, James Webb on the right. When we look at the Hubble image, we see the familiar browns and salmon hues that we see of Jupiter, as much as we would if we look through an amateur telescope at Jupiter. We think those colours are due to the fact that certain elements exist there, probably sulfur and phosphorus, that might be pulled up from the lower clouds. The bands indicate that there are very high winds going in various directions on Jupiter. And because there's lots of winds going in different directions, like on Earth, we tend to get storm systems. We still don't really understand why the Great Red Spot there is a storm system that seems to have been raging for 400 years. On Earth, storm systems come and go, and after a few days, they tend to dissipate. Why is it that on Jupiter, a storm system seems to have lasted 400 years? Studying that might help us understand weather a little better here on Earth. On the right-hand side, we have the James Webb, where we're seeing some different structures because we are looking at the infrared. We're still seeing belts of gas moving at high speed, winds moving at high speed around Jupiter. We're seeing different contrast because we're probably looking at different elements depending on which wavelengths of infrared light we happen to be using. And notice we have a flash of colour at the North and the South Pole as well. That's not an aberration because the James Webb doesn't have aberrations at that level. The fact that we're getting a little bit of orange at the top and the bottom indicates that we're actually seeing the aurora borealis and the aurora australis for Jupiter. Particles from the sun are getting caught by Jupiter's magnetic field and producing this glow there. Jupiter has a very strong magnetic field. Again, we'd like to understand exactly what's going on inside there. If we have a look at Saturn, the Hubble Space Telescope gives us lovely views of Saturn, even better than amateur telescopes can produce from the ground, of course, because we have the clarity of going above the atmosphere as well as a large aperture. So not quite as detailed as we would get by flying a spacecraft to Saturn, but this has the advantage that unlike a spacecraft, we can go and watch Saturn anytime we like. We simply have to schedule what time, how much of the Hubble Space Telescope or the James Webb we want to use for observing planets. We're not limited by a particular mission. We're not limited by the fact that Voyager only has a certain amount of time to view a planet before it moves on to the next planet, for instance. If we ask ourselves, what do we learn in terms of the difference between a Hubble view and the James Webb view? Working in the infrared gives us a view of Saturn which is at first rather odd. If we choose the wavelength appropriately, we can choose a wavelength in which the planet itself absorbs a particular wavelength. It absorbs lots of wavelengths. The planets themselves are made of hydrogen, helium, methane, etc. If we choose the wavelength such that the molecules in the planet absorb a lot of infrared light, then the planet itself comes out relatively dull. But the rings come out amazingly bright, because the rings are lots of icy particles, and those icy particles reflect light from the sun, whether it be visible or ultraviolet or infrared. The rings will reflect a lot of light. So when in the infrared, we tend to get this rather odd situation where things that we don't expect to be very clear, such as the ring system, suddenly become an awful lot brighter. And that's true when we look at other planets as well, like Uranus, for instance. Here the rings look amazingly bright, even though in practice they are extremely faint, which is why we didn't know Uranus had rings until relatively recently, and sending spacecraft there. But in this particular case, because again the rings reflect infrared light very effectively, the James Webb can show a huge amount of detail. And again, we have the advantage we can go and look at this planet anytime we like. When Voyager passed Uranus, it only had a few hours in order to take images before it moved on to Neptune. And during those few hours, nothing very interesting was happening on Uranus. There were no storm systems, and so it looked like Uranus was very dull. Now we've gone back to it with the James Webb, we find, well, actually there is a storm system raging on the left-hand side. That's why there's a bright spot on the left-hand side of the planet, and also the pole appears to be a lot brighter than the rest of the planet. We didn't appreciate this at the time because Voyager spent so little time there. But now we can go back and look at Uranus once a week, once a month, how often we like, as long as it's scheduled within the James Webb time. And a similar argument is true when we're looking at Neptune. Again, the rings of Neptune show up, very difficult to see in visible light, but relatively easy to see in infrared light. And in this particular case, as well as actually showing up some storm systems on Neptune, we actually see in the top part of this image what appears to be an enormously bright star, producing these star spikes, which is a function of the artifact produced by the hexagonal segments of the James Webb mirror. But when we look at that, that is not actually a star in the background. That's actually one of the tiny moons of Neptune, and yet it seems to be enormously bright compared to the planet itself. Same argument. The planet itself is actually absorbing a lot of the infrared light coming from the sun, but Triton, which is what this moon is, Triton, it's a large moon but still very small compared to Neptune. Triton is actually covered in solid nitrogen. It's effectively an ice moon, and therefore it's reflecting a huge amount of the infrared that's falling on its surface. So Triton comes out apparently very bright, even though it is very much smaller than its host planet Neptune. So what is coming next? Well, there are a couple of telescopes that are worth looking out for in the near future. The LSST, which went by the rather awkward name of the Large Synoptic Survey Telescope when it was first put together, that's effectively completed now. This is a picture when it was still under construction a year or more ago. That will be surveying the sky in what's called the Legacy Survey of Space and Time. They've chosen that name because that means that LSST is an acronym that they can keep. So lsst.org was the original web page of the Large Synoptic Survey Telescope. By naming this the Legacy Survey of Space and Time, they can keep the LSST domain. They don't have to pay for another one. So, and you can see the size of the camera here against a standard human there. This survey will be carried out for the next 10 years or so. The telescope is essentially complete and the survey will be starting shortly. And the idea of a survey is, unlike the Hubble and the Webb, which are told, go and look at this interesting object or go and look at that one, the survey is literally going to map whatever is out there. It's going to map the entire sky over and over and over again, which is why it's called the Survey of Space and Time. It's not just a survey of space, it's going to keep mapping the sky day after day after day after day, effectively night after night for the next 10 years. So not only will it find out what's out there, it'll also find out what is changing. Which objects are moving? Are they part of the solar system? Have we found new asteroids, for instance? As well as which stars are changing, which stars have changed their brightness, which stars have changed their color, which galaxies now have a supernova, etc. This Legacy Survey of Space and Time will be carried out over the next 10 years, and data will be released periodically, which will tell us about new objects that we never knew existed, and then other telescopes will go and follow them up, such as the European Extremely Large Telescope, hopefully operational by 2028, well under construction now. And again, it's a bit difficult to see, but there's a couple of people standing in front of it. Gives you an idea of the size. 39-meter diameter mirror. And again, there's a couple of people just standing on the platform that contains some of the instrumentation, the cameras, the spectrographs, etc., that will be collecting information. So the European Extremely Large Telescope will have a relatively small field of view. The survey telescope will find new stuff, and then the big telescopes will follow that up and look in detail at everything that's out there. So if I piqued your interest, you don't have to worry about these web pages. They're on the handout there. But the Hubble and the Webb are operational and producing some wonderful work, and the Hubble, of course, has been doing that for decades, the Webb only for the last few years or so. And it won't be long before the LSST and the ELT, the Extremely Large Telescope, will be online and producing wonderful data of their own. So if you want to know why these telescopes were built, what they've been doing, and what the future holds, go have a look at some of these web pages and find out for yourself. Thank you very much.
Thank you.